Assalamu alaikum. Welcome to the 8th lecture of natural language processing. So we are into the fourth, or in fact, the fifth week of the semester. And we have covered so far up to language modeling. We were discussing language modeling last time, and we will going to wrap up language modeling today. And then towards the end of today, we'll start with text classification. So in the previous lecture, we had talked about estimating probabilities, and we talked about the maximum likelihood estimate for probabilities, and we also discussed why MLE is not a good idea for language modeling. And we then started talking about some other techniques or more specialized techniques for estimating probabilities in natural language. And we will continue with that discussion today, and we will discuss 2 or 3 more ideas. And that will bring us to the end of n-gram language modeling. So after this, we will start with text classification, and we'll be discussing at least 2 uh, classification techniques, naive-Bayes and logistic regression. And of course, later on, we'll also talk about neural networks for language modeling as well as for classification. So, so that's the idea, that the agenda for today. So are there any questions? So, so we need to plan for our midterm exam as well. So, so I'm planning to have the midterm exam during the weekend 5 and 6 of March, which is after the 7th week of your semester. So, so it will be on campus, and 2 hours time slot. So we will decide the time and date through email and finalize it within this week, so that all of you know exactly when the midterm is scheduled. So if any one of you has some issues with the time, we can discuss that. But in general, we like to have a consensus time so that everyone can come and join the exam on campus. So, so any questions? So in the last lecture, we had started talking about advanced smoothing, and we also talked about interpolation, and we also talked about backoff. And all right, so we will start from there. So very quickly, just as a refresher, what was backoff? So backoff basically is if a probability or if a count or if a probability estimate is 0 for an n-gram. So if, for example, trigram is 0, meaning that the count of the trigram is 0, then use the bigram. Similarly, if bigram is 0, use the unigram. So if the bigram estimate is 0, use the unigram estimate. For example, if, for example, PWI given WI minus 1 turns out to be 0, you approximate that with simply PWI. So this is the back-off approach. And of course, if you have higher order n-grams, you are more likely to get zeros. Let's say you are doing the fourth order n-gram. If that is zero, you try the third order. If that is zero, you try the second order and so on. So this is the back-off approach. And then we talked about interpolation. So interpolation is basically um adding lower order bigrams to the estimate of higher order n-grams. Lower order n-grams to the estimate of higher order n-grams. For example, if you have a bigram wi minus 1, so basically this is simply your estimate for w for the bigram, which basically wi minus 1 wi divided by c wi minus 1 plus you add a proportion of the unigram estimate. So of course, this is for bigram, you're adding a weighted estimate of the unigram. If it was trigram, you would start with trigram, then add a weighted estimate of the bigram, then add a weighted estimate of the unigram. So it can be done recursively. So this is interpolation. And lambda has to be estimated on some training data set, on some corpus. So you train on a corpus and then you find a lambda that gives the best perplexity on a validation set, which is separated from the training data set. So once you have found that lambda, you do use that lambda in subsequent application of the model. So this is interpolation. Uh, and then we have some other variations. So for example, there's also something called stupid backoff. This is more common for very large scale corpora in which the number of the vocabulary size is tremendous, let's say web scale corpus. So in this case, in the simple backoff, we basically backed off to the previous n-gram. In this case, we do the same, but we also add a uh, add a reduction factor, and this is based on empirical analysis. So for example, uh, so 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 for example, you want to find wi given wi minus 1. If this is 0, of course, if it is not 0, then you do it in the standard way, which is wi and wi minus 1 divided by c wi minus 1. And so if this is 0, if this value is 0, then you estimate it with a constant which you have to determine, but this constant will remain the same, usually around 0.4 into probability of wi. Meaning that some constant, this lambda, you don't need to estimate every time for every data set, just fix it. Of course, in the standard backoff, there was no 0.4. You just used probability of wi. Here, based on empirical analysis, we found that usually you'll have to reduce the estimate of the lower n-gram to get a better estimate of the higher order n-gram. So the reduction factor here is 0.4. And this is generally fixed a priori and used consistently thereafter. So this is called stupid backoff. I don't know, the original backup should be more stupid because it doesn't have a factor there. So this is somewhat better, but in the literature, this is called stupid backoff. uh, so this was backoff. And then for very large n-grams, let's say web scale n-grams, you can do various other tricks. And I'll show this using the slides. Okay. So when you talk about web scale n-grams, what we are talking about is the number of types or the number of distinct, you can say, events of interest are tremendous, or the vocabulary size is tremendous. So in that case, you will have to estimate lots of probabilities. So we have to estimate probability for each type, right? Each event. So we can use some tricks here. So the first thing is pruning. So essentially, if an n-gram has a count greater than some, let's say, minimum count, let's say 2, 3, 4, or some percentage of the total vocabulary size, you store it. Otherwise, you don't store it. So again, this is space reduction. So if, for example, a higher order n-gram has a value which is meaningful above the threshold, let's say we are talking about bigrams. Let's say a bigram has a value of 10, count of 10. If it has a count of 10, which is, let's say, greater than our set threshold, then we will not keep its unigram. So for example, if we want to find the bigram is wi, comma wi minus 1. So for wi, we will not keep its unigram because its bigram is also sufficient count. It has sufficient count for the bigram. So we do not keep the unigram. The bigram would give us reasonably good estimate. So singletons basically means the lower order n-grams. So you can also do entropy-based pruning, which is based on how much disorder, basically how much disorder or inhomogeneity keeping all values would create in your data set. So this is kind of a more sophisticated way of pruning. So we won't go into the details, but you should know that this is a criterion to decide what to prune and what not to prune. Okay, so we would like to maintain a homogeneous set of estimates, which would help us do our calculation with the minimum amount of space requirement. And then you can talk about various efficiency things. You can use like efficient data structures, tree structures, like, for example, trie. You can use suffix trees or prefix trees. Again, the whole idea is to store things such that the space used is small. You can compress the storage. So Bloom filters is another example. And also, instead of storing words, whole words, because word, for example, the word, let's say, thing, T-H-I-N-G, if you store all of those characters, you will take up more space. If you give this whole word, T-H-I-N-G, a number, then that would take less space. So you can store numbers instead of words. So that will reduce your space requirement. And then, of course, you can also do, for example, probabilities are usually points. And they might be, you might have to retain them to a certain number of decimal places. So that would take space. So you can use other compression techniques to reduce the space requirement for that, like Huffman coding. Yeah, so you can quantize probabilities as well. So these are some ideas that are often used for very large scale n-grams. And most of these ideas are meant to improve computational as well as space efficiency on this slide. And of course, in the previous few ideas, we were basically using simple techniques for getting better estimates, back-off, interpolation, stupid back-off, and the idea of unknown as well. I think I mentioned this last time. So if a word does not occur in the training data set, uh, so if a word does not occur in the test set, so that would be considered an unknown word because there is no probability estimate for that word because you are developing that estimate from the training set. The training set did not have that word, so you won't have an estimate. So how to handle this? Basically, you designate some words in the training set as unknown, those words that have low counts, then get an estimate for probability of unknown. And then in the test set, whenever you see a unseen word, you use that probability of unknown. So this is also sometimes simply called UNK, U-N-K, in the NLP literature. And of course, this is also known as OOV problem, out of vocabulary problem. Any questions? So we have already discussed this. This is the stupid back off. So we are now moving on to discuss some other techniques. Advanced smoothing also had a problem of being a blunt instrument. We discussed this last time. So this primarily arose because there were lots of events or types that were zero, and probability mass was shifted from those events that did occur to those events that did not occur. And since the event that did not occur were in tremendous numbers, you distorted the distribution. So that's why advanced smoothing is again not considered reliable or robust for NLP, as well as the simple maximum likelihood estimate. So we are now going to discuss some other techniques. And basically, there are two ideas here, the Good-Turing and the Kneaser-Ney, and of course, some extensions of add one or add one smoothing. So we're going to discuss those now. So instead of add one, you can also do add k smoothing. The same idea, but instead of adding one for each event in your data set, for each type or for each bigram, whatever you're considering, we add k. And the formula is, of course, updated similarly. So probability of for bigram, Wi given Wi minus 1 is basically count of Wi minus 1 Wi plus k divided by, of course, C Wi minus 1 plus k into the vocabulary size. Of course, please put the parentheses. I did not put the parentheses there. The numerator whole thing is 1 unit. The denominator is also 1 unit. Okay. Okay. So we said that, and of course, if k is equal to 1, this is add 1 smoothing, right? And we said that add 1 smoothing is a blunt instrument. Uh, it's not appropriate for NLP. So here, if I put k greater than 1, would that be helpful in NLP? Actually, this would, if you take k greater than 1, which means that for each event, you're adding more than one additional events. And let's say if there's an event that is 0, you add 2 of them, for example, if k is 2. So which would take even more probability mass away from those events that did occur to those events that did not occur. So that is again not desirable, or that's even worse than k is equal to 1. So actually, in this case, we would like k, which is less than 1, is used for NLP. So you can use points. There's no issue in using non-integer values. So in general, for NLP, k would lie in the interval between 0 and 1. So in other words, you're adding, you can theoretically you're adding some fraction of an event, even if it did not occur. And as a result, maybe all the events that did not occur collectively might not take too much away from those events that did occur. So this is the add k smoothing, which is okay. You can say if you choose an appropriate k for NLP. All right. And then there are very slight variations of this idea, and they are known by slightly different names. So for example, you can have probability of Wi given Wi minus 1 as C Wi minus 1 Wi plus, let's say I've given it another name, M 1 divided by vocabulary size uh, yeah, okay, divided by, then we have C, I've mentioned what this is, plus M. So now in the numerator, we did not add K, we now adding M into 1 over V. What is 1 over V? So let's say 1 over V is if each word occur uniformly, then the probability for that word is basically 1 over V, which is vocabulary size. If all words occur uniformly. So basically, this is actually a probability, 1 over V, a probability estimate for any word in the data set, if we assume that all words have a uniform distribution. And then, of course, M is used to modify that. And the amount that you use to modify is then added in the denominator to make sure that the normalization is correct. So here, of course, we use the uniform word probability. You can actually use unigram probability as well. So for example, C Wi minus 1 Wi plus M probability estimate for Wi. This is a unigram estimate divided by C Wi minus 1 plus M. So you can say this is slightly better than the previous idea in which you use the same probability for every word. Here we are using the unigram probability for each word or for the given word. So these three ideas are extensions of the add-one smoothing, and they can be applied to NLP with the appropriate parameters M and K, and P. P, of course, is an estimate with appropriate parameters M and K. Any questions?
Sir, what is M over here?
जी जरा फिर से ऊंचा बोले, आपकी आवाज नहीं आई.
सर N क्या है यहाँ पे?
N किस में? M, अच्छा. M, okay. Just give me. So M is basically a number greater than 0. So you can, just like K, it's a number greater than 0, it's not necessarily an integer. So it can be used to tune the amount that you want to add to the count. So for example, let's say, so generally this M would be large, relatively large. So for example, let's say you have a vocabulary size of, let's say, let me say 10,000, 2, 3. Okay. So the uniform probability would be 1 divided by V, which of course would be 10,000, 1 over 10,000, right? So this is a very small number, right? And if you multiply this number with the number of uh, types, 10,000, if m is 10,000, then you get 1, right? Which is identical to then add 1 smoothing. Okay? But as I said, then m would be a larger number as compared to k, but it would still be less than the vocabulary size if you want to get good estimates. Okay? So if m was 10,000, 10,000, then it becomes add 1 smoothing. Okay? So in practice, m would be much less than 10,000. Okay? Does this answer your question?
Yes.
Okay. So now let's move on to the next idea, and which would lead us to the conclusion of this section. So advanced smoothing techniques are often based on heuristics, and those heuristics are derived from empirical analysis of the data. So most of these advanced smoothing, for example, has some theory in from machine learning, which means that you have applying Laplacian prior. Similarly, you can develop some more theory for ADK smoothing and even for the smoothing with uniform priors, uh, for unigram priors. But there is less theory for the techniques that we are going to now discuss, although they do give better results for NLP. And most of these observations are based on empirical analysis. So empirical, or you can say experiment-based smoothing techniques. Okay? So we will discuss two main ideas here. One is called the Good-Turing smoothing, and the other is the Kneaser-Ney smoothing. All right. And the Kneaser-Ney theory smoothing is the one that is most commonly used in practice nowadays. And it builds upon the idea of good Turing. So let's start with good Turing. So the good Turing idea is based on a simple observation. And maybe I can go to the slides. Let me see. So these are some advanced techniques that are now rarely used in practice, but they are mentioned here. But what we are going to discuss is the good Turing and the Kneaser-Ney. We have already discussed this. So we have already discussed this. We also discussed this. Okay, the advanced smoothing algorithms. So the intuition used by many of these advanced, so-called advanced smoothing techniques is that we should use the count of things that we have seen once. When I say things, these are like events, or these are bigrams, if you are estimating bigrams, or they could be trigrams or unigrams, whatever we are estimating. So use the count of things that occur once to estimate the count of things that do not occur. So out of vocabulary words or unknown words. So once you do that, you get an estimate for unobserved or OOV events. But since now, again, you're moving probability mass from observed events to unobserved events, you will have to adjust the observed events, the probability of the observed events. So that's the whole idea here. So let's look at the notation. So n underscore c basically is the number of things, or you can say events. I'm using these words interchangeably because events is a term that you use in probability theory. Things is anything that is observed. And in our case, there will typically be some bigram or trigram or unigram. So NC for C is the count of thing, and N is the number of times that we have seen things that occur C times. So let's look at this small data set. So I am Sam, Sam, I am, and I do not eat. So let's say we have this small data set. So how many times that, for example, I occurs 3 times. So this count of I, C of I is 3. How many times that Sam occurs? Sam occurs twice, right? And am also occurs twice. And then we have do one, not one, and eat one. So in other words, there are 3 things that occur once, there are 2 things that occur twice, and there is 1 thing that occurs 3 times. Okay? So if we use this notation, so what would N3 be? C is equal to 3. N3 is the number of things that occur 3 times. So how many things or events occurred 3 times? Just the word I. So N3 would be 1. And N2, number of things that occurred twice. There are 2 things that occurred twice, which is Sam and Am. Yeah, Sam and Am. So that is N2 would then be 2. And then N1, how many things occurred once? So there are 3 things that occur once: do, not, and eat. So N3 is equal to 3. Okay. So now so this, of course, is notation NC. So now let's look at another example in the next slide. So again, we are taking an example, you can say in terms of things or events rather than actual bigrams, but you can easily think of these as bigrams or unigrams or whatever is of interest in our NLP problem. So let's say you went for fishing and you caught 18 fishes. I don't know if fishes is a proper word or not, but 18 fish. So, and of course, the count of each species of fish is given here. So 10 carp, 3 perch, 2 whitefish, 1 trout, 1 salmon, 1 eel. All right. So what is N1 here? How many things occurred once, or how many fishes?
3 fishes.
3. So there are 3 things that occurred once. So let's say if we had, and of course, so if we use MLE, and I wanted to find the probability of, let's say, eel, for example, probability of eel occurred once. So if I use maximum likelihood estimate, the probability of eel would be 1/18, right? because it occurred once. And let's say the probability of car would be 10 over 18. But we are more interested or concerned with the unknown. So we start from the other side. So the probability of eel would be 1 over 18. Trout would also be 1 over 18 according to MLE. But let's say the next fish is some unknown fish. Let's say like bass, for example. So according to MLE, bass would be 0 over 18. ठीक है ना? But this might just be an anomaly of our small sample size. ठीक है? So we would like to assign, and of course, this is the whole issue of zeros and OOV. So we would like to assign some probability of bass. So what this approach says that we use the count of things that occur once to estimate the probability of things that never occurred. So in our case, N3 was, N1 was 3. So what was those? Trout, eel, and there was one other thing. I don't know, remember. Okay? So 3 things occurred. Okay? So the probability of some other fish that was never seen, some OOV event, or let's say some fish like bass, according to this approach, is simply 3 divided by 18. So we use the number of things that we did not see to estimate the probability of a thing that we saw once, to estimate the probability of things that we did not see. So again, we are moving some probability mass. Of course, this is very small amount of mass. So we have to adjust the other probabilities. So the adjustment for the other probabilities to ensure that all of them count to 1 or sum to 1 is again very simple. We compute the adjusted count, C star. So C star is essentially given as C plus 1 into NC, this is the numerator, divided by, NC plus 1. NC plus 1 divided by NC. So since we have taken some count away from the others, so we adjust the next level of observation count using this simple ratio, meaning the one amount that we moved there, we reduce from the previous one. So in this case, for example, let's say in our case was so 2 white fish, okay. Okay. So what is N2? N2 is actually 1. There is only 2 white fish. So only 2 white fish, only one thing that occurs twice. So N2 is 2, and of course, N1 is 3. And of course, N0, of course, there's no such thing N0, but an unknown thing, we have used some mass from the one things and given to unknown things. But we have to now adjust the one things by getting some mass from the thing that occurred twice. So that's what we are doing now. So let's say I want to whitefish occurred twice. So this was C is equal to 2, right? And of course, also know N2 is equal to 1. Okay? So let me find C 1. Okay? So let me want, so you can say adjusted count of C is equal to 1. So that's what I wanted to count. So this would be C star is equal to, C is equal to 1, 1 plus 1 into N2 divided by N1. So this is according to the formula that we wrote there. So what do we have here? We have 2 into what is N2? There is just 1. Okay? So divided by what is N1? 3. What do we get? 2 over 3. Okay? So instead of using 1, we have now reduced its count to adjust for the mass that we gave to unobserved things to 2 over 3. So now our estimate for, let's say, trout, which occurred once, trout के spelling क्या है? T-R-O-T-R-U-T, trout, would then be 2 over 3 divided by 18. All right. So instead of 1 over 18, which was MLE, we are now getting 2 over 3 into 18. And since now we have reduced this, we now move to the next level to adjust all the masses. And of course, we will have all those probabilities summing to 1. So you notice that the number of things that do not occur, as we have seen before for English, as we saw for example, Shakespeare's writing, the number of bigrams that did not occur were in the millions. So we simply took the number probability mass from the things that occur once and give all of them to the millions of unobserved events. So again, the mass transfer is very little as opposed to, let's say, add-one smoothing. Okay? And you can continue in this fashion. Similarly, let's say if you want to find C is equal to 2 ka C star nikalna, C star would then be 2 plus 1 N3 divided by N2. And you continue in this fashion. Okay, now one thing here. Yeah, I just wanted, I don't know, इसमें figure नजर आ रही है सही? Let me draw it myself. So let's say, basically, if you plot NC with C, you will get a heavy tail distribution, meaning that if C is equal to 1 small, you will have many things that occurred 1 times. But as C increases, let's say C is 300, you will have fewer things. Let's say if you again talk about bigrams, there will be fewer bigrams that occurred exactly 300 times. And similarly, as you increase C to, let's say, 1000 or 1500 or 2000, So how many things occur 2000 times? So that would be generally very small number, 2, 3, even 1, or sometimes even 0. So what happens is, and by the way, this distribution occurs, it's a very common distribution in nature. And this was one of the intuition behind the good Turing idea. Take the mass at the higher count and give it to the lower counts. You won't change the distribution significantly. So there will be many things that occur few times, let's say 1, 2, or 3, but there will be only 1 or 0 things that will occur many times. So usually as C increases at higher Cs, and if you plot this, you might have 1 here, then 0, then 1, then 0, 0, 0, 0, then again 1, then 0, 0, maybe 2, then, and so on. Okay, ऊपर चले गया. Just a second. So let's say again, what happened?
Sir, pen नहीं select हुआ हुआ.
Pen नहीं हुआ हुआ, ठीक है. Just give me a second. Okay, अब लिख रहा पेन. Text message कहाँ से आ गया? Just a second. Controls कहाँ से आ गया? एक second. ओके, ये एक्चुअली कोई और चीज खुल जाती है. Okay, what I was mentioning is okay, ये हमेशा मुझे पेन तंग करता है इसके साथ. I don't know why this is doing so. Actually वो उसकी विंडो सामने आ जाती है, ये जो जूम की. ये जूम की विंडो खत्म हो गई है.
Yes, sir.
अच्छा, ठीक है. अब मैं करूँ तो अब क्या होता है? या दैट्स फाइन. अब लिख रहा है ना
सर अब मेरा हाल कलर नहीं select हुआ हुआ कोई.
जी?
पेन तो आ गया बट कलर नहीं पेन का कुछ select हुआ हुआ. मतलब आप जब ड्रॉ कर रहे हैं ना तो कुछ बना नहीं आ रहा. Yes.
अब सही.
Now we
ठीक
can
है.
see. Yes.
ठीक है. So if you increase C at high levels of C, you might, let's say if you have a bar chart, you might have a 1, then there might be several zeros, again 2 maybe, then 1. So it might be very jumpy. So you can then fit a smooth line, which is a power law line, to this and get estimates for the C's instead of those zeros and ones, which might give you poor estimates. And this is only for the case when C is large. For smaller values of C, as we saw before, 1, 2, and 3, usually NC would be very large and you'll get very good estimates. Only for the higher values of C, those counts would be jumpy in the sense that you might see C is equal to 1 or C is equal to 2 or C is equal to 0, 0, 0, and so on. To adjust for that, you can fit a smooth line. So you can fit a power law smooth line and then get the estimate from the smooth line to get the values of C, and from there you compute C star. So this is the good Turing approach for estimating. So if you look at the resulting numbers for some practical data set, actual count. So if the actual count is 0, C star, of course, is 0, 0 something. And if actual count is 1, the C star is 0.44. And if actual count is 2, 1.26. So 2.24, 2.2, 3.24, 3.22, 5.19, and 6.7.24. So you notice that the reduction in count is now it's kind of not significant as opposed to when we saw for advanced smoothing. And the reduction in count, secondly, is very stable after C is equal to 3. So in other words, you don't really need to do this calculation explicitly. Maybe simply you subtract some constant D from C and get the new estimate. Okay? And that's the idea for absolute discounting. And this is the idea that Kneaser-Ney used in addition to a couple of other ideas. So let's look at that. So this is the table again, just to highlight. So you can, instead of computing C star using the approach that Good-Turing mentioned, you can simply use a constant D for all values of C greater than 3, and that could be about 0.75. So C minus 0.75 would give you C star. And maybe for the count of 2 and 1, you can use some other value. So sometimes you just use 0.75 as D, or maybe you choose 2 or 3 Ds. And then you're done. You don't need to do the extensive calculation. So simply discount the count that you have observed and compute the estimate using that. So that is the one idea that Kneaser-Ney used. The other idea is that Kneaser-Ney approach is an interpolation-based approach. So remember what was interpolation? Let's say if you have bigram, you estimate bigram plus some parameter lambda multiplied by the unigram estimate, right? So the bigram estimate is computed using absolute discounting as using D. And then Kneaser-Ney also proposed a different way of computing the unigram probability and the lambda. And that lambda need not be estimated from training data. It can be calculated directly. So let's look at that. So now we are going to need so 3 ideas. One is absolute discounting. Second was interpolation. And third was unigram probability, or lower n-gram probability. So what is absolute discounting for bigrams? So Wi minus 1. So simply we do max minus D and 0 divided by, of course, C Wi minus 1. So what have we done in the numerator? In the numerator, we simply have C star divided by C ठीक है, और C star हमने किस तरह निकाला? Simply by minusing D. Of course, if after minusing you get a value less than 0, you retain the value 0. That's why you have the max there. ठीक है. So for example, if the original C count was 4, you minus 0.75, you get 3.25 and divided by the unigram count of the context, which is CWI minus 1. ठीक है. So this is called absolute discounting. And main thing is based on the Good-Turing intuition, but made it simpler by not computing all those counts explicitly. The second thing was interpolation. What do we have? We need to have some lambda of Wi minus 1 multiplied by probability of Wi. ठीक है ना, ये इंटरपोलेशन में ये पार्ट आता है. ठीक है. ठीक है. So let's look at first of all PWI, the unigram estimate. So instead of using PWI, he also used another heuristic, and this is also again based on empirical evidence. He said instead of computing PWI, which would, of course would be what? CWI divided by N, which is the total number of observations or total number of tokens in the data. Instead of that, he said you should compute P continuation probability of Wi. So what is this probability? Let's look at that. So let me write the formula first, estimate, and then I'll explain the intuition. Okay. So let me maybe show you the formulas from my slides or notes we have. Can you see this document?
Yes, sir.
Okay. So this is, I've written the Kneaser-Ney formula here. Okay. The first part is, of course, the absolute discounting. The second part is the interpolation, lambda, and the unigram probability. So the unigram probability is given by this formula here, P continuation. Let me so the numerator is Wi minus 1, which is the context. And of course, this is the number of unique So what does this mean? See, Wi minus 1 comma Wi is greater than 0. This means that we are counting, Wi is the word of interest. We are counting Wi minus 1s for which this Wi is a continuation. And we are counting how many such continuations actually occur in our corpus, observed. So that's why it's greater than 0. And then we divide with all observed bigrams. Here we are, of course, considering bigrams. In the denominator, the sum of all bigrams or is the number of distinct bigrams that occur, meaning that CWJ minus 1, CWJ is greater than 0. So what is the intuition behind this? So what did we have? We were counting wi minus 1, unique wi minus 1, for which wi is a continuation. This is the numerator. So let's take an example, the example as given in the slides as well. Let's say San Francisco. So Francisco is wi, and San is the continuation. San is the preceding word, right? And Francisco is the continuation of San. So we are talking about probability of Francisco given San, right? So what we have there is we want to find how many. So San is how many preceding words. So wi minus 1 wi. So wi minus 1 Francisco. So how many wi minus 1 exist in the data set for which Francisco is a continuation? So that is the numerator. So in this particular example, can you think of any word off the head for which Francisco would be a continuation? So San is one of them, but there are very other few words that for which Francisco would be a continuation, right? So San is one of them. Maybe in the numerator, we just find one. San is one. So in the denominator, we have all bigrams that are non-zero in our data set. We are not counting those bigrams that do not occur. We are only those counting, for example, if you remember the Shakespeare data set, only 30,000 bigrams were used. 30,000 was probably the vocabulary. Yeah, I think 30,000 bigrams were used. I don't remember, but the actual number of possible bigrams were in the millions. Okay? So only those bigrams that were used would be in the denominator. So this would give you an estimate for the unigram probability of this. On the other hand, if you had used Francisco count, which might occur many times, for example, San Francisco was used many times, okay? And you divided with the total number of n, which might be also a very large number depending on your corpus size, that estimate would be a poorer estimate according to Kneaser-Ney. And that value would generally be smaller. So this value, the continuation probability is based on observed events only, not on unobserved events. Remember, unobserved events in NLP are tremendous. They distort the distribution. So here we are looking at how many times Francisco is a continuation of a distinct word in the numerator, which is observed, and in the denominator, how many observed bigrams exist, or the total possible bigrams, and in the numerator, the bigram that contain Francisco. So that's how we estimate this value. So bigrams containing Francisco, or let's say, let me say wi, divided by all existing bigrams, meaning they're all bigrams that are non-zero. So this is the continuation probability. And the second interesting thing that Kneaser-Ney did was he computed lambda directly, and that could be computed directly because of the discounting. So remember, we discounted the previous counts. So based on that discounting, you can compute lambda directly. So lambda would be d divided by actually d. So discount was d. So d, how many counts did you discount? D in dw cw I minus 1. And then, of course, what was the numerator? So we wanted to find w. इसमें या फिर देख लें फॉर्मूला से sometimes a bit. Yeah. So lambda is basically d C wi minus 1 into the count of the bigrams So we wanted to find how many bigrams for which this wi minus 1 is non-zero, meaning that how many bigrams have wi minus 1 as the preceding word. So why are we interested in wi minus 1? Because this is the amount that we had reduced from the previous expression where we subtracted minus d. So we subtracted minus d from c wi minus 1 wi, उसमें से reduce किया था ना हमने, और हमारा उसका जो normalizing factor था wi minus 1 था. So we wanted to find how many wi minus 1 में से d हमने subtract किया, तो वो हमने multiply किया ऊपर. तो कितने wi minus 1 थे जिसमें से हमने d subtract किया, उतना हमने यहाँ add कर दिया, d into that number. And of course divided by वही जो हमारा normalizing factor था. So this formula, you don't need to estimate any parameter from data. All parameters can be computed directly, and it gives you reasonably good estimates. And this is the approach that is most popularly used in practice if you're using n-gram language modeling. So ये जो वर्ड डॉक्यूमेंट है ये भी मैं शेयर कर दूंगा, इसमें मैंने मैथमेटिकल नोटेशन में ये लिखा हुआ है, स्लाइड्स में भी फॉर्मूलाज दिए हुए हैं. आई वुड स्ट्रांगली रेकमेंड कि आप इसको एक दफ़ा गो थ्रू कर लें, बिकॉज आई नो थोड़ा सा ये कंसेप्ट कंफ्यूजिंग है, बट if you look into it in bit more detail, it just all makes logical sense and it would give you normalized probabilities. ठीक है? So 3 things have been used: absolute discounting, rather than using Good-Turing approach to find the C stars, we simply subtract D. Second thing, interpolation and unigram estimates. Unigram estimates, or the estimates for the preceding n-gram, is based on continuation probability, which we look at if you're talking about a particular word, let's say Francisco, we look at how many contexts appear for which Francisco is a continuation. That's the numerator, and divide by all such contexts that actually appear in the data set. So that's the unigram estimate. And then the lambda is simply computed by the amount that we have reduced from the counts, and we have given it to this unigram estimate. So D into the number of bigrams for which we have reduced D, divided by, of course, C wi minus 1. Sure. We're also running out of time. Actually, this brings us to the end of language modeling, n-gram language modeling. The next main section would be text classification, which I believe we would start next time. Any questions? Any questions? No questions? Meeting controls are not available. ठीक है. Any questions? No questions? So we do have a quiz in the next lecture, at the end of the next lecture. So we are continuing with our routine for a quiz every week. So you will also get your next assignment later this week. And as I said at the start, I'm planning to have the exam on the 5th or the 6th of March. And in a 2-hour slot, of course, you will have to reserve about 2 hours and 30 minutes. Exam would be 2 hours long. And so let me know if you have any specific comments regarding the exam date and time. Otherwise, I'll send out an email and let inform you about the exact date and time. Okay, so let's end the session then.